Hi, in this video, we want to take a look at making predictions with spatial statistical models. All right, so we're going to go over some examples from Applied Spatial Data Analysis with R, second edition. Here are the authors, and here is the website. So Applied Spatial Data Analysis with R-book.org. All right, and you can download this book for free through UCF's website if you're a student. All right, so now what we want to do, we want to talk about spatial predictions. So our model is going to be a little bit different than a linear regression model. All right, so when I make a prediction, so here Z is the variable that I'm interested in modeling. S sub 0 is the location that I'm making the prediction on. X are my predictor variables, my covariates in a linear regression sense. S sub 0 is the location. S, so this part here, S is the locations of my observations for the data that I'm using to build the model. Z is the value of the variable that I'm interested in at the locations. And here, X are the values of the covariates at location X, S, location S. And then here, this is my coefficients. All right, so what's happening here is that this is the prediction coming from a linear regression model using the covariates at the site. Okay, now what we're going to do, we're going to take a weighted average of the residuals at all of the locations for the individual spot. All right, so this is the residual at location S of that linear regression model. V is the covariance matrix of the variable of interest at the locations I have measurements. And then little v is the covariance vector between my observed values at the locations and the location of interest. All right, and then here, oh, this should be an exponent -1 right there. That's an error. That should be exponent to the v. This is the formula for our coefficients for beta hat. All right, it works out that this model is a best linear, unbiased predictor for the value at the location. All right, so think of this as a linear model plus a weighted average of the residuals is how to think about it. Now, we're going to have prediction error. And what that's going to be, oh, this should be a plus sign. Oh, I'm full of errors this time. All right, this is a plus sign. The prediction error variance is going to be the variance of the target variable by itself plus this term coming from the covariance plus this quadratic form on X, then covariance matrix X inverse. And here is the definition of that delta. All right. And the error variance for beta hat minus beta is going to be this X transpose V inverse X inverse. So here, this is our error variance term on the covariance involved in this quadratic form. All right, so let's talk about some types of Cricking models. So Cricking, Crig is the last name of a student who proposed this in their dissertation, and a lot of the literature credits his advisor for much of this, but the name stuck with him. So we call this Crig or Crigging models. A lot of times in literature, you'll see it with lowercase k because this is such a frequent type of modeling that we go ahead and drop the big K to little k because it's so common, so frequent. All right, so there's a couple types that we have. We have Crigging with external drift. Here we have one predictor variable, and here we don't consider coordinates at all when we work on this. Universal Crigging is just any time that we have p greater than 0, so I have one or more covariate predictors. Ordinary Crigging, we have prediction, predictor variables, none, but we have the intercept going on. So this x sub 0 equals 1 says that's the intercept model. Now, simple Cricking. In this situation, we assume that we actually know what beta is, what our coefficients vector is, and we run with that. Now, one thing that tends to happen when people are actually doing this is they'll take beta hat, plug it in for beta as if it was actually the true value instead of an estimated value in simple Cricking. All right, so let's go ahead and let's run through a few easy examples. So let's go ahead and fit simple, ordinary, and universal Cricking models on log of zinc. Okay, so here, let's do simple Cricking. What I'm going to do, I just take the Crig function from the GStat package. I specify the formula that I want. So you'll notice this is log of zinc, depends on the intercept. I'm using the data set for the locations. Now here, this is where I want to make my estimates, is my new data. And if I have a variogram that I want to include, which I don't have to, I put I fit the variogram. And now here, this beta equals 5.9. This is my a priori knowledge of what's going on. This is why it's simple Cricking. And something that's very nice about this, about the GStat package, is that it actually spits out what type of model it is for us after I build it. That way, you know for certain that you're being consistent with, with the literature, how they intend it. All right, so now let's do another one. Let's do ordinary Cricking. So here, I've got my GStat Crig, same formula, same locations, same new data, same variogram, but now I'm not specifying what the coefficient is, or I'm not specifying what the intercept is. And so it's being fitted. I have 0 predictors. I'm just using the intercept. And so we can see that it's ordinary Cricking. Let's do another one. Now this one's universal. Okay, on this one, I'm going to do a square root transform on my distance covariate. Same locations, same new data, same variogram, and it's going to give me universal Cricking because I have one or more covariate predictors. All right. Now, how does the predict function work with this? Okay, so there's a lot of different types of models in the GStat package. All right, so when I pass an object in R to a method, what the function does, it looks at what type of object was passed to me. Then it goes and it finds a function under the hood to drop that object into to give you your output. So when you run the predict function, you're actually tapping into potentially a whole collection of different functions. And so this decision tree shows us like how the GStat predict function works through all of the possibilities. So is it a variogram? Yes or no. If it's not, is there a trend function? Yes or no. No, it goes to inverse distance weighted interpolation. If there is, so it's not a variogram and it has a trend, then it does trend surface prediction. If it's a simulation then it will check to see, is there a, no, it'll check for trend coefficients. So simple Cricking, co-Cricking. If it has only intercept, it could be ordinary or universal co-Cricking. And then, for simulations, does it have indicators, sequential Gaussian simulation, or sequential indicator co-simulation? And so there's a whole bunch of different ways that the predict function could grab and run through what's there. All right, so let's think about multivariable prediction, co-Cricking. All right, so co-Cricking incorporates autocorrelation of variables, and multivariable cross-correlation and spatial variability can be correlated with other variables. All right, so this one's different than standard regression. So the previous two, that's not really that surprising, but spatial variability of a variable can be correlated with the value of other variables. So the observed value of this variable can be correlated with the variability, the variance of this variable over here. Huh. Okay, so this is a more complicated, structure for what's going on. All right, so when we tell the GStat package to do this for us, it automatically checks to make sure that there's no negative variances. So negative variances can arise if the data and model combination really are incoherent. So if I see negative variance, we know that variance can't be negative, but if the computation gives me a negative value, I know something is off. All right, so now let's go ahead and extract predicted values from a co-regional linear model. All right, so what I'm going to do is during previous videos, I built up this co-regional linear model with multiple variables. And so this is a linear model of co-regionalization. Everything's good. It's ordinary co-Cricking. And so now here I get my output, and you'll notice that I've got the predicted value and I've got the variance going on here. So prediction, variance, prediction, the variance. So it's every single time we have the pair. Then after we get through that, we have the covariance between the variables. Now let's go ahead and visualize the predicted values for the co-regional linear models. Notice that I've got a whole bunch of different ones. So 1, 2, 3, 4, 5 covariances. And then we also have, so here we have 4, 5, 6, there's 10. All right, so we've got our variances and our covariances are being plotted here. So the diagonal will be those variances, and then the off diagonal will be the covariances. And so here we can kind of get an idea of what's going on. I would think it would be best to look at these individually, not on a common scale. More than likely, from like after you're done looking here, if you want to have a more precise image. Now, something we can do, I can adjust the range of one of the submodels, so that way I can get a more precise of what I'm looking for. So when I look at the model for the log of cadmium and lead, I can just change the range by defining it this way. And now, if I want to, I can extract the predicted values from the multiple variable linear co-regulation model just by using the predict function. Now, when things get kind of complicated, I can just say, hey, don't check it. So the set parameter in the GStat package is how I go in and I adjust the under the hood aspect of different models. And so the set, if you look at the help documentation, you actually have to go to the our CRAN's help documentation. There's a website that has further, the author calls it standalone, the standalone documentation, if you want to start reading up on this. So if you need to get deep in the weeds and under the hood on it, that's where you need to go to read up on this. So this is saying just don't do a check. So here, or actually no, it is doing the check for us. And it's using the Cauchy-Schwarz inequalities. All right, so what this is doing, this is just checking this does not, so the lack of failure does not mean that there's not a problem, but a failure would indicate a problem. So this is one of those situations where if it detects a problem, you know there's a problem, but these checks, if it does not detect a problem, that doesn't mean there isn't one. So we have to use adult supervision to know if this is going on. So this is not 100% informative checks. And this is talked about in the textbook. And now let's take a look. What's the names of what I get from the output? So I can see X and Y's locations. I get predictions and variances for each location, and I get the covariances for each of the combinations. All right, so another thing I could be interested in is co-located co-creating. All right, so this is just a special case of co-creating where the predictor variable is available at all predictor locations, but instead of choosing all observations of the secondary variable, we only use the secondary variable at the prediction location. Okay, that's a lot of words. What's happening? If I have, let's say I've got a whole bunch of different locations. In the standard way of approaching this, if I have 5 locations and I want to estimate at one of them, in my modeling, what I would normally do is that all 5 locations would be involved in modeling the location of interest. Okay, so what this is doing is this is saying don't use 4 out of the 5. Don't use the 4 other locations, only use the one that I'm interested in. So here, what normally happens is we would be incorporating a predictor covariate for all locations we have measurement for. If I don't want to do that, I'm going to be using the co-located co-Cricking. In this situation, I only use that covariate value at the location that I'm interested in, and I ignore that covariate's values at all other locations. All right, so now to do that, I'm going to do the gstat function of the gstat package. G is null because I'm setting things up. Here's my ID. I'm saying log zinc depends on the intercepts. There's my locations. Here's my model. Now here I'm setting up some distance aspects. So I'm going to take the distance between points minus the average plus log of the zinc. And here I'm just setting up the variogram model that I've got. I'm going to get this ratio of variances going, and then I'm going to rescale the PCL term of the variogram by this much. And now for my co-located co-Cricking model, what we're going to do, I'm going to take this model here, I put it in for G. I say, hey, I've got distance n going on. Depends on the intercepts. I'm going over the grid. Now here, I only want 1 point. So I'm saying it has to, the distance has to be, at the one location. So I'm using distance because I only want the one spot. Here is that model, this rescaled, or so the variogram with the PCL term, the parameter rescaled, and then I'm going to merge log zinc and dist n together. All right, and so now I am just setting, I'm going to take this variogram, and I'm going to adjust the PCL term. Now this time, I'm taking the square root of the PCL times the PCL of the other one, and then I multiply that square root by the correlation between these. And I'm dropping this into the co-located co-Cricking model, and then I get my predictions. So it's a lot of steps. It's grinding out. Ultimately, the punchline is just a special specific model structure. And it just takes, takes a bit to get this going. All right, so now let's go ahead and compare the 3 models. So I've got, I've got 3 different models. I've got co-located, or ordinary, and universal. So I've got my collated Cricking. I'm going to tack on the universal model's predictions. I'm going to tack on the ordinary Cricking predictions. And now I'm using SP plot to go ahead and print. So here's the object. I specify which variables I want plotted, and then I just name them. And this is specifying the color cuts. So I want 8 different colors, 7 cuts. And so we can see a difference between these. They're similar but different. And we'd have to look at the individual performance and subject matter knowledge to know which one would be best. All right, now change of support. What's going on here is we're talking about the situation where either I have points that I built my model on, but I'm interested in regions, so like polygons, or I have polygons and I'm interested in points. All right, so point kriging is where we model at individual points, and block kriging is where we average over regions. All right, so averaging has a lot of advantages for us because we know that the variability reduces. If the variability reduces, we have more confidence in our model. And this can also be useful if I have point modeling going on, but I need to give models, let's say, by county, by neighborhood, by state, by city, something like that, averaging over the region of each of, let's say, a neighborhood would be a good way to reduce the variability and improve communication with my stakeholders. All right, so we have 3 ways to perform this for block kriging. We can, one, for regular blocks by specifying a block size. For irregular blocks, but constant blocks, by specifying points that discretize the irregular form. And for blocks or areas of varying size, by passing an object of class spatial polygons to the new data argument. And so like, for example, we'd be replacing me use grid with spatial polygon. All right, so let's do an example of ordinary block kriging for 40 by 40. So here, I'm saying the block parameter, everything else is similar to what we've done before, but now I'm saying 40 by 40 blocks. So I'm saying, and now the default setup is going to give me rectangular regions, and it's going to do its best to make everything nice and pretty, work well. There's no reason why we'd necessarily need rectangular, but that's by default, and it is a very natural way. Another way that we can approach this is by limiting where the model is, or what region the model is being built up on. So for this example, we're going to set up a circular shape with radius 20 centered on our points, and then we're going to build our model. And so here, you'll notice that I've got all these points. I'm only taking the ones that are within a certain distance of the center, and I'm specifying the blocks this way. So this is a way for me to do the block modeling. I can also do over spatial polygons. And so how this will happen if I drop a polygon or polygons into this system, what it will do, it'll average out the model over each of the sub polygons I dropped in. All right, so let's go ahead and grab the Muse area data sets. And now here, as it comes out of the box, that's not a polygon. What I'm doing in this code here is I'm converting it to a polygon. Then when I have it as a polygon, so this will be a polygon of the entire sample region on this one. So it's going to be rather coarse, but I know the variability will be low. I'm going to drop that in for my new data. And so here, I'm taking the formula, I'm taking the data, I'm taking the model. When I say the new data is a polygon, it's automatically going to do the averaging for me. And so let's go ahead and plot that just so that we can see. And so here we can see the polygon of the entire sample region, and we have it averaged out over what we have for over the region. Now, if I want to, I can go through and I can discretize any polygon using the SP sample function in the SP package. All right, so if I want to sample points over a polygon, I can use this function. If I want to make sure that I have this discretized polygon, I can set the regular parameter for us and it'll for type, and will provide a grid of points. All right, now the other ways I can sample, if I want to, I could do random, regular, stratified, non-aligned, hexagonal, clustered, or Fibonacci. For this purpose, it would make sense to do regular. And so here, this is, I specify the, the polygon and then number of points. Here's an offset necessary, and I say regular. Boom, it gives it to me. All right, I'm going to stop the video at this point. Take care and goodbye.